Hello student, hi, good evening. So today we are going to see new topic. So that is about Schottky diode. What the name is Schottky diode. Schottky Schottky diode. Okay, Schottky diode. Today we are going to discuss about Schottky diode. What is Schottky diode? Why we need Schottky diode? Okay, why not normal PN junction diode? What is the purpose that we are going to see this Schottky diode? Okay, Schottky diode. Why we use Schottky diode? First of all, Schottky diode why we use, so because it has some advantages. Schottky diode has some advantages as compared to the normal PN junction diode. Okay, as you know very well, the normal PN junction diode, which can be used as a switch, which can be used as a reactification, which is used for reactification of the signal, and which is also used for switching purpose, and normal PN junction diode, and that is also for light emitting diode. Okay, so LED. So these are what the advantages that we got in normal PN junction diode. Okay, so if you see PN junction diode first you see PN junction diode. In PN junction diode, if you see here, in PN junction diode, this PN junction diode is what it is able to rectify what low frequency signal. Okay, so this PN junction diode, and this my Schottky diode, and this PN junction diode is able to rectify the signal up to low frequency. Okay, up to means low frequency signal, it is able to rectify. But as we go for high frequency signal, then this PN junction diode is unable to rectify. Okay, it will not work as a rectifier for high frequency signal, and its speed is also less, means switching speed is also very less as compared to Schottky diode. But in Schottky diode we are not getting that problem. Okay, so Schottky diode mainly using for what? Using for the purpose of high speed switching, and the purpose of for rectification of high frequency signal like radio frequency signal. Okay, radio frequency signal. Then how? The question will come, how we can rectify. Okay, so now see, so that you can see here how we can achieve these advantages through Schottky diode. So let's see I have one signal. Okay, I have one signal of 50 hertz, like 50 hertz of signal. Okay, I have one signal of 50 hertz. Okay, so this is my 50 hertz signal. Let's say this is 1 volt, this is minus 1 volt, and this is 10t, and its frequency is about 50 hertz of signal. Okay, so now I want to rectify this signal through normal PN junction diode. Okay, so then here I am able to rectify it very easily. Okay, if I will apply this signal at the input of this diode, normal diode. Okay, so and I am able to rectify this signal. Through this normal PN junction diode. So that is like this, and here this. Okay, so here through PN junction diode, the signal of frequency about 50 hertz, 50 hertz. I am able to rectify this signal. Okay, very easy. Now come to high frequency signal, like in the order of megahertz or hundreds of kilohertz signal. If I will increase the frequency of this signal, okay, if I will increase the frequency of this signal, high frequency signal. So now I will see what will come. What is the output of this normal PN junction diode? What is the output of this normal PN junction diode? If I will see this, see here, it will come like this. It will rectify, but it will take some portion of negative cycle also. Okay, so this is not a DC signal. Okay, it's not a pure fluctuating DC signal. This is what AC signal. So this is the problem where we are stacking. Okay, so we are unable to rectify this high frequency signal. So this frequency, let's say this is in the order of 100 kilohertz, 100 kilohertz of signal we are unable to rectify. Okay, so how, what, why we are unable to rectify it? As you know very well, this diode, this is a PN junction diode. Okay, why this problem, why this problem is coming with PN junction diode? First of all, understand that why this. So why we are not, why we are unable to rectify a high frequency signal through PN junction. Okay, so first of all, understood that why. So this is because, as you know very well, as you know very well, PN junction diode, PN junction diode. Okay, so this is my anode and this is my cathode. Okay, so this is my P side and this is my N side. Okay, so this is my P layer, this is my N layer, this is my N layer. Now, as you know very well, in case of PN junction diode, in case of PN junction diode, this diode, this diode is what? There is no biasing at all. So this is unbiased. This is what? Unbiased diode. Unbiased diode. Okay. Under thermal equilibrium condition, what happened? Under thermal equilibrium condition, so there is some processing that is happening within this device, within this two terminal device. That is what? There is a diffusion. Okay. So diffusion process. In diffusion, the majority charge carrier that will migrate from higher concentration to lower concentration. Okay, so this everything is happening under what? Under unbiased condition. Okay, unbiased condition. We are not biasing this device. Okay, so we are not biasing this device. So due to which there is what? Like in case of n-type, in case of n-type semiconductor, the majority charge carrier, if you will see, let's say this is my N and P. Okay, better to write here. So this is my N and this is my P. So N side majority charge carrier are what? Who? Electron. Electrons are majority charge carrier. And P side majority charge carrier are what? Hole. Majority charge carrier are hole. Okay, hole. So now now this electron, now this is high concentration. Okay, so minority charge carrier are hole here in N side and minority charge carrier are electrons in P side. Okay, so when the device is what? Unbiased, then there is what? Unbiased means in unbiased condition there is a some processing that is happening within the device, that is nothing but a diffusion process. In diffusion process means the carrier, there is a migration of the charge carrier from higher concentration to lower concentration. Okay, so this is like here is a higher concentration to lower concentration. Okay, so wherever there is a difference in the concentration, definitely there is a diffusion. As you know very well, whenever there is a difference in the concentration, then there is a diffusion. There is a diffusion process. Means migration of this charge carrier from higher concentration to lower concentration. Means here electron will migrate from N side to P side and hole will migrate from P side to N side, P side to N side. So there is what? This charge will flow like this. Okay, from higher concentration to lower concentration, lower concentration. Okay, so hole from P side to N side and electron from N side to P side. So when this diffusion happen like this, then after that what happen? Actually it is, so means electron is going that side, means there is what? There is a positive charge, means it is donating. Okay, so it is donating the electron to P side. Okay, so then there is a positive charge, means these are donor ion. Okay, so donor ion. So now there is a negative charge because it is accepting the electron. There is a acceptance. Okay, so these are accepting the electron and donating the hole. Okay, so these are what? Ion. These are positive and negative ion. Okay, so when there is a positive, then when there is a positive and negative ion, these are positive. So let's see simply for understanding purpose, there is a positive ion and there is a negative ion. Okay, so when this ion will get formed, then there is a what? There is a electric field. Okay, so there is a establishment of electric field. Electric field will get established. Okay, so across the junction, there is a establishment of electric field, and due to this electric field, it will stop further movement of this electron. Okay, it will stop the further movement of this charge carrier from P side to N side and from N side to P side. So therefore there is a what? Therefore there is a due to this electric field, there is a appearance of what? Depletion region. So depletion region will get formed. So due to electric field, due to this establishment of electric field, the depletion region will get formed across the junction. Okay, so there is a depletion region formation across the junction. This is positive and negative ion. these are positive and negative ion. Positive ion at n side and negative ion at p side. P side. So there is a formation of depletion region. Now we are now now you are confirmed that how it is happening. It is under what unbiased condition. Unbiased condition, there is a what unbiased condition, there is a process like diffusion. Because unbiased condition, there is a difference in the concentration. Okay, concentration difference means if we see the electron concentration, n side is higher, p side is lower, definitely there is a diffusion process. Okay, this diffusion will takes place until and unless that difference in concentration become zero. Okay, become zero. So therefore this diffusion will run up to that time. Okay, so until the difference in concentration will become zero. So due to this diffusion, there is a migration of charge carrier, and due to which the migration of charge carrier means it is giving the electron from means electron is moving from n side to p side, means there is appearance of what positive ion, and similarly there is appearance of negative ion. Once this ion will form, then there is a establishment of electric field. Due to this electric field, there is what due to this electric field, a depletion region will get formed across the junction. So there is no further movement of this charge carrier. Okay, so this is what depletion region. And this depletion region, there is a potential barrier whose potential is what whose potential is about 0.7 volt. Whose potential is about 0.7 volt. Okay, so we have to apply the biasing. Okay, so we have to give the biasing of about zero point 0.7 volt, so that it will cross this junction, it will cross this what threshold, and the device will start conducting. Okay, so this is for understanding purpose, means how actually the actually device conduct. Okay, so device conduct for conduction. In order to make the device conduct, so we have to bias the device. Okay, so that is the process of charge carrier movement that is flowing within the device. Okay, so when the device is unbiased condition. So that we have seen for p-n junction diode. This potential barrier that we have seen in p-n junction diode, potential barrier is how much? So this is my depletion region, and this side, this is my p, and this is my n, and this is my negative, this is my positive. There is ion, and there. Okay, so there is a majority charge carrier electron, and there is a majority charge carrier hole, and this is my depletion region. Okay, and this depletion region has potential barrier, potential of you can say about 0.7 volt. So that's why we have to bias this with, like, okay, we have to bias this. So in order to conduct, so in such a way that this device will start conducting, so we have to bias with potential of at least 0.7 volt. Now coming to what, why it is unable to rectify the high frequency signal. So that is simple. See here, if I will give high frequency of signal like this, high frequency of signal to what, to this normal p-n junction diode. Okay, to this normal p-n junction diode. This is my p, this is my n. Okay, so these are electron. There is hole, majority charge carrier hole. These are electron, and if you see, this is my depletion region. Okay, across this there is a positive ion, and there is negative ion at p side, positive ion at n side. Okay, so now see, when I will apply this signal of frequency about 100 kilohertz, let's say frequency of about 100 kilohertz, if I want to rectify this signal, then what happens? As you know very well, when these charge get when I will apply the biasing to this device in order to conduct it, so in order to make the conduction through this device, so if you see here, this is my positive and this is my negative. Okay, so during positive cycle, see, during positive cycle this device will conduct. Okay, this will conduct, and there is a flow of current, so it's okay during positive cycle. Okay, now during positive cycle, these charge carrier will move like electron. So focus only one carrier. Okay, so only one carrier. Let's say during positive bias, see, during positive cycle of this input signal, this electron will move from n side to p side. Okay, so let's say this is only one electron. For understanding purpose, I am saying that just focus only one electron. Okay, so this electron has moved from n side to p side, okay, during first cycle. Now see, during negative cycle this polarity will get changed. Okay, so now this is negative, this is negative, this is positive, this is positive. So now see here, so this is negative, this is positive, this negative, and this now this electron will act as what, minority charge carrier in p side. Okay, so then it will move from p side to n side, p side to n side. Why? Because electric field is in that side, where electric field formation is from n side to p side. Now this electric field will support this minority charge carrier, because the electron that has moved from n side to p side during forward wise, during this positive cycle, now it become minority charge carrier on p side. During negative cycle it become minority charge carrier. So therefore during negative cycle this electron will come back to n side. Okay, this electron will come back to n side. So this is what minority charge carrier. Okay, so during forward wise it is majority charge carrier which is moving from n side to p side. Now this same charge during negative cycle will act as a minority charge carrier which will move back to its original position. So because while coming back to its original position, it will take some time, okay, it will not come within a fraction of second. So it will take some time. That time is larger, than this time period of this signal. Okay, so time period of this signal, the time taken by this minority charge carrier to come back to its original position is larger than the time period of this signal. So that's why it is showing what, if you see at output side the waveform will come like this. Okay, during negative cycle also it will still conduct during negative cycle. Why it is conducting? Because of minority charge carrier, that has got stored during the positive cycle. Now coming back, they will take some time, and that time is nothing but reverse recovery time. The reverse recovery time is what, much larger than the time period of this signal. This is the purpose why we are unable to rectify the high frequency signal through this normal PN junction diode. Okay, so now I think your doubt is clear, why we are using Schottky diode. So main purpose is this. Okay, main purpose is here only, because positive cycle it will rectify. Okay, so no problem during positive cycle, but during negative cycle, only for high frequency signal, this time period of this signal will get decreased. Okay, so this time period of signal is very small. Okay, very small, in the order of nanosecond. But here during negative cycle, the charge carrier which has moved during forward wise into p region will act as a minority charge carrier. Okay, so then during negative cycle this minority charge carrier is like a stored charge carrier. Then it has to come back to its original position. Okay, for that it requires some time. Okay, it will take some time. That time is nothing but reverse recovery time. Reverse recovery time is the time taken by the stored minority charge carrier to come back to its original position. And this reverse recovery time is much larger than that of time period of this high frequency signal. So that is the reason that we are unable to rectify high frequency signal. Okay, high frequency signal. Then in the picture, Schottky diode come into the picture. So it will rectify, and it will sort out the problem of rectification of high frequency signal. Okay, so that is the reason that we are using Schottky diode. Now we will see in Schottky diode, is this problem is still in Schottky diode. This we are going to see. Okay, this we are going to see, because first of all you have to make yourself much stronger about this why it is happening. It is happening because of this minority charge carrier. Because in PN junction it is a bipolar junction. Okay, it has minority charge carrier, it has majority charge carrier as well as minority charge carrier. Okay, because during reverse wise, the time taken by the stored minority charge carrier is much greater than, much larger than the time period of high frequency signal. Okay, so that's why it is what, it is still conducting during negative cycle. It is still conducting during negative cycle, and therefore we are unable to rectify the high frequency signal. For that purpose, we are using what, Schottky barrier diode. We are using what, Schottky barrier diode. Now see Schottky barrier diode, Schottky barrier diode. Now this topic, now actual discussion is there. Okay, actual discussion is now. Now see here, this is my Schottky diode. Okay, so this is my Schottky diode. What is Schottky diode? As you have seen, this is my M metal, and this is my N. Because at P side I have what, replaced. P side I have replaced with M metal. Okay, so M metal. So metal. So now this is my Schottky diode. This is my Schottky diode. This is my anode, and this is my cathode. Anode, cathode. Anode positive, cathode negative. Cathode negative. Nothing. It is similar. It is exact similar to what PN junction diode. Okay, PN junction diode with respect to what? With respect to structure. Okay, with respect to structure, but its operation is somewhat different. Its operation is to means different from normal PN junction diode. Okay, so it has some advantages that we will see. Now see here, this is my metal. This is my metal like platinum and molybdenum. So these are the form of metal that we are using in Schottky diode. Okay, so this is my P side that I have replaced with metal. Okay, so metal. Now P side is no longer here, so this is only metal, and this is my N type. So now see here, this is my N type. This is my N type semiconductor. This is N type semiconductor, and this is my metal. This is my metal, and here also let us suppose first this two terminal device, two terminal semiconductor diode is what, open circuited. There is no what, there is no biasing at all. There is no biasing at all, and same process will happen here also. So this electron, this N-type semiconductor is highly doped electron. Okay, so highly doped semiconductor. This N-type semiconductor is highly doped semiconductor, which has majority charge carrier electron, and metal itself is a sea of electron. Okay, so there is a sea of electron, means in metal there is a lot of electron. Okay, lot of electron. So therefore, now see what happened. So similarly here also the diffusion process will occur. Okay, in unbiased condition. This is under thermal equilibrium concentration. Okay, under thermal equilibrium, some diffusion processing happen within this device, where the majority charge carrier, start flowing from charge carrier will start flowing from higher concentration to lower concentration. Means there is a migration of charge carrier from higher concentration to lower concentration. But now the confusion is that metal also have a lot of electrons, lot of charge carrier, and heavily doped semiconductor also have lot of electrons. So now which electron will start moving from where to where? Now here actually the electron, the majority charge carrier that is present in N-type semiconductor will start injecting into the metal. Why it is? It is because in highly doped N-type semiconductor, the electrons get higher, and electron has higher energy. Okay, they are feeling like higher energetic because the density of electrons is very large in case of metal. So that's why the electron inside the metal has less energy. They are less energetic compared to the electron in N-type semiconductor. Okay, the electron in the N-type semiconductor are more energetic. Okay, they are more energetic. So that's why they are able to inject inside metal, because they are not that much tightly bound. Okay, so tightly bound by each other as compared to metal. Metal has lot of electron. Okay, so therefore under unbiased condition, these electrons will start injecting from N side to P side. Once they will start injecting, they will start moving from N side to P side. Then what happens? As you know very well, there is a formation of what? There is a formation of ion. So these are positive ion, and where they are moving, so this is negative ion. These are negative ion. Okay, from n side to p side. At n side positive ion, at m side there is a negative ion. There is a negative ion. See, these are negative ion. Negative ion. Okay, in unbiased condition. This is the case of unbiased condition. So due to which there is a what? Due to which there is a establishment of electric field. So electric field will get established wherever there is a positive and negative charge. As you know very well, there is electric field. Definitely there is a electric field. These positive and negative charges are immobile ion. Immobile ion, which means that they are unable to move. They are unable to move. So therefore there is establishment of electric field. Once the electric field will get established, then there is a formation of depletion region. So depletion region will get formed, okay, across the junction. Now this electron, now this depletion region has potential barrier of about 0.15 volt to 0.15 volt to 0.3 volt. Okay, so this is the potential barrier. This is the threshold that we have to cross. By applying the biasing in order to make this device in conduction state. Okay, in order to make the device in conduction state, we have to apply the biasing of about 0.15 volt to 0.3 volt, and then we are able to conduct. Okay, so then this device will able to conduct. Now up to this story is same. Up to this the story is similar to PN junction. Okay, so nothing, processing is same, higher concentration to lower concentration, diffusion process in unbiased condition. Then here we have seen also that depletion region here also form, because whenever the charge is moving, there is a formation of ion. Wherever there is a formation of ion, there is a establishment of electric field. Once the electric field will get established from positive to negative side, then there is what? Then there is a formation of a depletion region. Now this depletion region will stop the further movement of this charge carrier. Okay, so this charge carrier. So now see, up to this the process is similar to PN junction. Now during reverse wise, if you see the during reverse wise, there is no minority charge carrier at all. Okay, so but there is no minority charge carrier. During reverse wise, the current is only due to what? Uh, thermal excitation of electron in the metal. But in case of Schottky diode, the reverse bias current in case of Schottky diode is due to only the thermal excitation of electron with thermal generation of electron within the metal. Okay, so there is a thermal generation of electron in the metal during reverse bias, due to which there is a reverse bias current, and that reverse bias current is very large. Okay, so but that current is not due to minority, because now the point is that there is no minority charge carrier. Okay, in case of Schottky diode, there is no minority charge carrier at all. Okay, so there is no minority charge carrier at all in Schottky diode. If you see Schottky diode, okay, so now in Schottky diode, now we will see this we have seen. Okay, so this we have seen. So there is a depletion region. Okay, so this is what? Positive ion on n side, positive ion on n side, and negative ion on p side. Okay, so negative ion on n side, and means metal. Okay, so this is my depletion region. And this is my cathode. This is my anode, and this is my cathode. Okay, so this is my depletion region. Now what we will see here, what we want to see here. So the problem that we are facing in case of PN junction diode, that high frequency signal. Here also I am taking high frequency signal. Okay, I am taking high frequency signal of whose frequency is about 100 kilohertz. Okay, whose frequency is about 100 kilohertz, and at the output of this device, of this Schottky diode, I am getting the waveform like this. Okay, so means this Schottky diode is able to rectify this high frequency signal properly. Okay, so now it is a pure fluctuating DC. Now I can say that it is a pure fluctuating DC. Okay, so this is So this is the advantages that we are getting in case of Schottky diode. Okay. So from here we can say that the Schottky diode is used for high frequency application, like high frequency application. Okay, because it is able to rectify this signal. It is able to rectify this high frequency signal. Why? Because there is no minority charge carrier. Because when we apply during during positive cycle, this device will on. Okay, so it will turn on. This Schottky diode will turn on. Okay, so then it will conduct. During negative cycle, if you see, during negative cycle, there is no minority charge carrier at all. Okay, there is no minority charge carrier, means it will get off. Okay, it will off. It will not conduct. It will not conduct for negative cycle. Okay, it will not conduct for negative cycle. Why? Because there is no movement, because there is no minority charge carrier that is present in the Schottky diode. In Schottky diode there is no minority charge carrier. Okay, it is a therefore we can say that it is a Schottky diode is a unipolar device. Okay, Schottky diode is a unipolar device, and Schottky diode is also known as what? Hot carrier diode. Why hot carrier? Because the electron that is present in n-type semiconductor they are highly energetic electron. The electron which is present in the n-type semiconductor are highly energetic, and they are able to inject inside the metal. So that's why this Schottky diode is sometimes also known as what? Hot carrier diode. Hot carrier diode. Now we are able to see here there is no minority charge carrier, there is no minority charge carrier at all in the Schottky barrier diode. Okay, so due to which the reverse recovery time of this diode is very small, due to which the speed of this device is very high. So that's why it is also used for this Schottky diode is also used in high speed switching circuit, like logic circuit and CMOS circuit. So because there is also very high speed switching, so very high speed switching requirement is there. So for that we are using Schottky barrier diode. Okay, Schottky barrier diode. These are some advantages that we have found here. Okay, so you have seen high frequency signal, how it is amplifying, how it is rectifying this signal very easily. Okay, so why it is happening? Because of what? There is no minority charge carrier at all. Okay, so therefore it is a unipolar device. No minority charge carrier means reverse recovery time is very small. It is approximately equal to the time period of this signal. Okay, so that's why it is unable to conduct during negative cycle. Okay, it is remains off for negative cycle, and it will properly rectify this high frequency signal. So this is one of the advantages that we got in case of what? Schottky barrier diode. Now, so if you see the structure of this Schottky barrier diode, so these are the advantages that we have seen in case of Schottky barrier diode. What is the advantages? Why we are using Schottky barrier diode? What type of advantages that we got in the Schottky barrier diode as compared to the normal p-n junction diode? Okay, so this is what Schottky barrier diode. Okay, so if you see, this is my silicon dioxide layer. Okay, silicon dioxide layer. This is layer structure for Schottky barrier diode, and here is a metal. This is my metal. Okay, so and here is nothing but anode. This metal side is anode, and here is n-type substrate. This is my n-type semiconductor. This is my metal, and here is my cathode, which is negative. Anode is positive. So this is layer structure for what? Schottky diode. This is my metal anode. This is my cathode negative, and this is my n-type semiconductor, which is heavily doped semiconductor. Okay, so heavily doped semiconductor. And if you will see the symbol for this Schottky diode, so this is like this. So this is the symbol of Schottky barrier diode. Symbol is this. This is my anode, and this is my cathode. Okay, practically if you will see in laboratory, so you will get the Schottky barrier diode like this. Okay, so here is a some silver color. You will found one silver color. This is my negative side, and this is black color. This black color, there is a, this is like anode side, and this is cathode side. Okay, cathode side. So you can identify like this. So this is what, this is this is device that we will get in the laboratory for Schottky barrier diode, and this is a symbol of Schottky barrier diode, and this is layer structure for Schottky barrier diode. Okay, Schottky barrier diode. And we have seen what, and here in case of Schottky barrier diode, if you see in case of Schottky barrier diode, so here Schottky barrier diode, in Schottky barrier diode you will get what, you will get what type of contact, ohmic contact. Okay, ohmic contact. There is a ohmic contact. You will get in contact, ohmic contact in case of Schottky barrier diode, and non-rectifying contact, which are non-rectifying. Okay, non-rectifying. So this is ohmic contact, which is non-rectifying type. It is a non-rectifying type. Okay, so this contact is non-rectifying type contact. Okay, so non-rectifying type contact, this is ohmic contact in case of Schottky barrier diode. And normal PN junction diode, if you will see normal PN junction diode, for normal PN junction diode, this is my normal PN junction diode. Here you will see what, you will see non-ohmic contact. Here is non-ohmic contact, and rectifying type. These are rectifying type. Okay, so this is rectifying type. Yes, this is non-rectifying type. Non-rectifying type we will get in Schottky diode, which is ohmic contact, and rectifying type, that we will get normal PN junction diode, so which is non-ohmic contact. Okay, non-ohmic contact. This is all about this Schottky diode. Okay, Schottky diode, what we have seen in Schottky diode. So where Schottky diode is used, Schottky diode is used in high frequency signal, high frequency application, and which is able to rectify the high frequency signal, and it is also used for high speed switching as a high speed switching device, which is used in logic circuit, like in CMOS switching circuit, that we are using Schottky diode. Okay, so in Schottky diode we have seen that it is a unipolar device. There is no minority charge carrier at all, because of which there is a reverse recovery time of this diode is very, very small, and due to which it is able to turn on and off with very high speed. Okay, so it is a high speed switching device, and it is also able to rectify the high frequency signal. Okay, so in the absence of minority charge carrier. Okay, so that is only the problem, because during negative cycle, the minority charge carrier, that stored minority charge carrier, that takes some time to come back to its original position, and with that time is nothing but reverse recovery time, which is much larger than that of time period of a high frequency signal. So that is the problem, that we had faced in case of normal PN junction diode. Okay, so this is all about Schottky barrier diode. Okay, so thank you very much. Okay.